Mm-hmm. Sure.
All right. Welcome everyone to the IFT-SAIFR Colloquium. We're happy to have Fernando Brandão today, who is also giving lectures this week on entanglement and related issues. He's a native of Belo Horizonte, I think. And okay, he got his PhD from Imperial College London, and then he stayed a bit more at Imperial College as a postdoc. Then came here to UFMG, where he then was assistant professor. Then he went back to Europe as a senior researcher at the ETH in Zurich, and he also went back to University College London. For a while, he was researcher at the Quantum Architecture and Computation Group at Microsoft. And Roger was pointing out that now there is also some Google connection. And since 2016, he's been the Brent Professor of Theoretical Physics at Caltech, associated with the Institute for Quantum Information and Matter, which is an NSF Physics Frontiers Center. In 2013, he got the European Quantum Information Young Investigator Award, and I quote, for his highly appraised achievements in entanglement theory, quantum complexity theory, and quantum many-body physics, which combine dazzling mathematical ability and impressive physical insight. So he's interested in quantum information, entanglement, the connections also to other areas like many-body systems, statistical mechanics, etc. So he's going to tell us about quantum computing in the near term.
Okay, thanks a lot. It's a pleasure to be here. Thanks for the invitation. It's my first time at IFT. And I'm very impressed with the institute. It's also my first time in São Paulo, believe it or not, but I'm happy to be here. Yeah, so I work at Caltech, but I'm on 1 year leave at Google. It's nearby to Caltech, actually. Both are in great LA. And I guess during this talk will become clear what I'm doing at Google. Right, so the question I want to address is whether quantum computing is something very far ahead in the future, right, that we have to wait many decades until it realizes, or if it's something that we might start seeing already in the near term. And I will connect that, I'll address this question in some very concrete way with research I have been doing in the past 2 years, but we'll get to there. So just as a motivation first, why we want a quantum computer, right? So one good motivation is that quantum is hard, right? In the sense that suppose we look at the use of the Department of Energy supercomputer by area, and this is like a plot, right? Then you can see, material science is like 15%, lattice quantum chromodynamics 7%, chemistry 15%. And so, all these areas, based on what they are solving Schrödinger equation, right, for many particle systems. So a large part of this Department of Energy supercomputer power is devoted to simulating quantum physics, right? And if we can get a better handle on the simulation problem, that will be good, right? We could do, we can find better drugs, we can maybe understand quantum chromodynamics better, and so on. So why this is the case, right? Why it's so hard to simulate these quantum systems? There's a lot we could say about that, but the most basic explanation, I think, is just that if you have a quantum state, psi, on n qubits, right? A qubit is just like a 2-level quantum system. Then this is a vector, right? It's a unit vector on a complex vector space of dimension 2 to the n, right? So we have just some bases. It can be like spin up and down bases, for example, for each spin. But then you need all these coefficients, right? See I sub 1 up to I sub n. And there are 2 to the n different coefficients, and they are just complex numbers, right? So we need 2 to the n complex number to describe a quantum system of n particles. So there is this exponential growth in the complex to describe a quantum system in terms of its volume, right? And that's why, at least if you just want to do Schrödinger equation, the evolution or compute some ground state properties in the most naive way, just using linear algebra, this is not scalable, right? This takes a lot of computational power. Of course, there is a question if there is more efficient ways of doing that, right? Like clever ways. And that's a lot of theoretical physics about that, right? But as far as we know, there is no general way of doing better than just paying this price, this exponential price. And this has been around, right, for a long time, maybe since the early beginning of quantum mechanics. But people didn't really appreciate this question for a long time, or at least they didn't know how to formulate this in the right way, right? So for that, you have to be interested in computer science and quantum mechanics at the same time. Right nowadays, it's a commonplace. It wasn't back then, the beginning of quantum theory. There was no computers, right? But one of the first to point this out was Feynman, right? And he has some very influential lectures that he called Simulating Physics with Computers. There's a lot of great insights there, and one of them is this passage. It says, trying to find a computer simulation of physics seems to me to be an excellent program to follow out. Nature isn't classical, damn it, and if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy, right? So it's a great quote, right? And what is his pointing out to? Well, he's pointing out to this idea that maybe, right, we should just build a quantum computer if you want to simulate quantum physics, right? So you just should use the laws of quantum mechanics to build a new kind of computer, and maybe this exponential complexity that I alluded before, it will not appear if you have this different kind of computer. So that's basically the idea, right, of a quantum computer. What we want to do, we want to use well-controlled quantum systems for performing computations, right? And I'll tell you a little bit more concrete what I mean by these well-controlled quantum systems. But there was these early ideas by Feynman, for importance. Then there was some pioneers of the field like David Deutsch, that his motivation for quantum computation was actually to prove, that there is this many-word interpretation of quantum mechanics is correct, right? He says, okay, if you can have this exponential speed up of a classical computation, the only explanation is that we have many universes and the computation is spread out across these universes, right? So unfortunately, people didn't buy this explanation, but yeah, it was his motivation. But what really kicked off the field, I think, was this discovery by Peter Shor, now from MIT, back then from HCNC. What he saw is that using this computational model, I'm going to describe more in the sequel, but in this computational model, there is an exponential speed up over classical computing for if you want to factor big numbers. Okay, so here's the problem is, I give you a number, for example, 15, and then you have to output the prime number factors of it, so 5 times 3 in that case. So that's easy, right, we learn in school, but suppose I give you a 1,000-digit number, okay? Then of course we cannot do it in a piece of paper, right? But actually our best computers cannot do it either. So the best algorithm that we have for factoring grows as exponentially the number of digits, which I call n to the power of 1 over 3. Okay, so it means that like 1,000 or 2,000 digits, it already takes too long, you cannot do it. And that's, okay, it's a basic problem, it's nice, but it's also a fundamental problem because the fact that we think it's very hard to factor numbers, classically, hard from a computational point of view, people use that to build crypto systems, right? And the most used one, it's called RSA, which we use all the time to buy stuff online and so on, is based on the hardness of factoring. So if you know an efficient way of factoring, then you can break all these crypto systems, right? So there is a lot of stake. And what Shor found is that if you have this quantum computer, this new kind of computer, you could factor in n to the 3 time, where n is the number of digits. Okay, so you could basically break all crypto systems that we use, at least the most used ones at the moment. So what is this model? This computational model is we want to mimic what, one way to think about classical computing, of course you can have like, if you know, we can define using Turing machines, that it's kind of nice, but it's cumbersome. The best way to define classical computing is just to think of the physics, right? Basically what we have is a bunch of bits, they can be in 0 and 1, and then each time we just choose 1 or 2 of the bits and we apply some very basic logic gates there, right? Either do an OR or an AND or some control knots, something like this. And what we want to do in quantum mechanics is the same, okay? So this is a 3-qubit quantum computer with 7 quantum gates. And this has been like implemented in the lab, for example, using superconducting qubit. But the idea is that we have these very controlled quantum systems. For example, they could be superconducting qubits, and this is just whether this is related, for example, for superconducting qubits to the number of excitations into superconducting island, the number of Cooper pairs there. But if it could be also the polarization degree of freedom of some photon or something else, right? It's just a 2-level quantum system. Then we start, they are completely independent, the 3 of them, And then we start applying these basic building blocks. So this H is called Hadamard gate. Doesn't matter what it is, but this just is unitary on 1 qubit, right? So basically you tune on a Hamiltonian on this 1 qubit, and it undergoes some unitary evolution, like Schrödinger equation, and we do the same to the other qubits. Then they also have to interact, right? This interaction is important, but we only need what we call a 2 qubit gates. So this again is a Hamiltonian here that we switch it on, but only acting on the first 2 physical systems, and we do nothing to the rest. And then for a short while, it implements some other quantum gates. And then we keep doing that, okay? And then we keep doing that for a sufficiently long time. So in this case, the circuits, if I would tell you what this H and this control phase is, it generates this cat state, like this GHZ state. But you can, right, you can come up with a different circuit that maybe does a different task, right? And the way Shor found his algorithm is just to write down some more complicated circuits, which would be something like this, for factoring, right? So it doesn't, I won't explain how it works, but he came up with it, right? And of course then, eventually like to implement that, but you see it gets more and more challenging, right? We need more qubits, we must have full control over them, we have to execute a lot of control in time, and also, most importantly, they have to be very protected, right? If there is noise here, it's unclear if the computation will work as well, right? So in principle, we can do that. If quantum mechanics is correct, we can do that. And we are trying to reach this regime, but we are definitely not there yet. Okay, great. So factoring is a good application, right? Maybe you can say, well, it's kind of malicious, right, to build a quantum computer just to break other people's secrets. But it's not the only one, right? And that's good, right? This talk will be about quantum algorithms, right? So what is the stuff that we can do on a quantum computer, at least partially. And we can break, there is people, right, it's an active area of study, quantum algorithms, and we can break into 3 classes of quantum algorithms. One is what we call exponential speedups. Is when we have an exponential separation in the running time of the quantum algorithm with respect to the best classical one. And here, simulating quantum physics, the dynamics, at least we think is an example, right? Going back to Feynman. Again, just a clarification. This is all, we are arranging all complex theory. This is all like unproven assumptions. Right? It could be that there is an efficient algorithm to simulate all quantum systems. We do not know that. We cannot prove that it doesn't exist. But it seems unlikely given all the research that people have done in the best method that we have, right? So these are not unconditional results, but as far as we understand, we could have exponential speedups to simulate quantum physics on a quantum computer. There is Shor's algorithm for factoring, of course. We're going to see later that we can solve linear equations much faster on a quantum computer too than classically. Then there's some other problems for which we know we can prove there cannot be exponential speedups, but there is still some polynomial speedups, and that might be relevant, right, one day. And one example is just this Grover algorithm. This is a very simple problem. You're just given a list of n elements, and there is one marked element there. So if you want to find your friend's, I don't know, phone number in some catalog, right? We don't really do it anymore, but maybe your phone wants to find in the database, right, that it has there. And classically, if you don't have any information about this list, you just have to go through it, right? So it takes times n, linear. In quantum mechanics, you can do in square root n time. So there is a square root speed up, and we know it's the best we can have, right? So there is a speed up, but it's smaller in that case. And then there's a third group, which is, there's a lot of heuristics. So there is a lot of methods that we would like to try it out on the quantum computer eventually. And they might give very good speed ups, maybe even exponential, but we don't know yet. So there is called quantum annealing, where you want to solve some combinatorial optimization problem by Adiabatsky evolution, for example. There's some discrete version of it called QAOA. There's many applications nowadays in quantum machine learning, but we don't know yet, right, if they're going to pay off, but they might. And then you can ask, when we're going to start running these algorithms, right? And then say, okay, maybe this exponential speed up might take 25 years. So it's when we can build this universal quantum computer for factoring, for example, 1 million qubits, right? Or 10,000 qubits. But they have to be logical qubits, right? Because there is error. So we need error correction on top of it. So in the end, it's a quantum computer with around million or 10 of millions of qubits, right? Which is very daunting, right? But maybe one day we'll get there. Then you say, what about polynomial speedups? Maybe it's even longer, right? Because we have to build the quantum computer and it has to be cheap enough, right? That just this polynomial speedup is already, or this quadratic speedup is already, it already pays off. How about these heuristics? The funny thing here is first never, right? Because we don't know. But maybe much sooner. And this is one point I want to make, right? So there's a lot of these things that people already start trying, and there is reason to believe that maybe some of these will pay off in the near term. So a challenge of course, is to find more algorithms in each one of these 3 classes, and to see when we're actually going to run this application. So, oh, by the way, feel free to interrupt me if you have any question or want to say anything. You don't have to wait to the end. Okay, so this is this idea of these early quantum computers. My colleague from Caltech, John Press, he gave a name to this. He called this like the NISQ era, and this name has stick. So this is called the noise intermediate scale quantum regime. And the idea is the following. So as I mentioned, we're still a long time away from having a quantum computer which is capable, for example, of factoring a 300-digit number, right? So this will take a long time. But early quantum computers, and when I mean a quantum computer, let me clarify, is like a computer with around 50 to 100 qubits, no error correction, but low enough error rates. Maybe error rates of like 0.5% for every 2 qubit gates, right? So I haven't specified what it is, but just just think about that. You know, whenever you apply a 2 qubit gates, it's perfect, and you can apply it 200 times until you see 1 error, right? So this is the level of noise that people can have now. And there are many people trying. There is Google with superconducting qubits. They are almost there with like 72 qubits and the 0.5 error rates that I mentioned. That's the goal for this year or next year. Then IBM is trying a similar approach. Harvard is doing experiments with neutron atoms, with some optical traps. They have 51 qubits. It's a different model. It's hard to think in terms of circuit model, but it's interesting nonetheless. So there is all this new, right? There is all these new quantum experiments available. And one question for the theorists, right, like myself, is can we use these NISQ processors to do anything interesting, right? So of course they're great experimental achievements, right? And really shows that there is progress in the area, right? So, but is already interesting from the point of view of computation or not yet? We have to wait to have more qubits and error correction and so on. And then people start exploring this idea of what we call a quantum supremacy. So the idea is, as I mentioned, we probably cross the regime where quantum devices offer computational speedups over classical computing with around 50 qubits, and that's what we call quantum supremacy. So, so what I mean speedups? Well, I just mean they're in this regime where simply we cannot simulate by brute force anymore the quantum system on the classical computer, right? With around 50 qubits, or around this, like 50 or 55, something like this, depends on the computation. It just takes too much, okay, memory and computational time to simulate them classically. So we're in this regime where we cannot predict what the experiment will do, right? But we can still run the experiments. So what people have explored is to come up with very artificial problems, like problems related to sending a bunch of non-interacting bosons through some optical linear network, or just applying some random circuit and measuring all the qubits in the ends, which are not interesting per se. No one cares about this problem, but are problems that you can run on the quantum computer correctly, at least to high level of accuracy, but for which we have no idea how to solve them classically as well, right? So for example, if the problem is just simulate the output distribution of a random circuit of 50 qubits, if you have the 50 qubits, you can just run it, measure, and you're sampling from the distribution. At least like, you know, a noisy version, because there is noise, but we have a good control over the noise. Whereas classically, we have no idea how to do that, okay? And that's the goal for now. So we want to reach this regime, and then we say, okay, our quantum computers, small quantum computers, doing something that we cannot do classically anymore, right? So I think that would be a very interesting benchmark, right? So we haven't, we're not there yet in quantum computing, but it's not the end of the story, right? So the first question after that is, this, like this random circuit or Boson sampling proposals, I mean, why you want to solve them, right? So they are not solving a useful problem, right? So is it already interesting, this quantum device, in the sense of the long-term idea of quantum computing? Can we use them to solve a problem that we really care about, right? Or at least someone cares about. And then these heuristics come in, right? So there is some heuristics that we will try when we have these quantum computers, and try them soon. So we can try, for example, quantum annealing. Is this idea of trying to solve some combinatorial optimization problem using adiabatic evolution, quantum mechanics, for example. But then here, there's a lot of research, and it shows negative results. It shows that there is a classical method called quantum Monte Carlo that might work just as well as the quantum computer, because these are very particular kind of physical models. They have like what is called, they don't have a sign problem in quantum Monte Carlo language. So there is this drawback here. There's some applications in quantum chemistry. Basically, the idea here is to try to compute with better accuracy the ground state energy of some molecule than what you can do with traditional quantum chemistry methods. In the long term, for quantum computation, this, is in the direction of quantum simulation, and it might be a nice application. But for now, there's some proposals using basically create an ansatz, a variational eigensolver for the true ground states, and you optimize over the parameters. But there are some drawbacks here. So in particular, the sampling complexity for achieving chemical accuracy, which is the goal here, is very big. So this might not be possible either. We are kind of in this situation where we would like to have more things to try, right? So we like to find an application which is on one hand, beyond quantum supremacy, is about some problem that people care about. But on the other hand, we have a more firm basis to believe that the quantum computer indeed is doing a better job than just a smart classical algorithm, right? So that's the goal. And then I come to the problem that I have been studying, which I think might be a candidate for that, which is this semi-definite programming. Okay, so let's just see a little bit of math for a little bit. So this is a class of convex optimization problems, and it's the following. So you have, this should be capital M, sorry. So the problem is you want to maximize trace Cx with the constraint trace Ajx is smaller than Bj and x bigger or equal than 0. So x is an n by n matrix and is the variable you want to optimize over. So you want to optimize over matrices. And this bigger or equal than 0 means that it's positive semi-definite. So it should be Hermitian or in the real case symmetric and all eigenvalues bigger or equal than 0. Okay? So you have this constraint on your variables you want to optimize. You want to optimize over positive semi-definite matrices. And you want to optimize a linear function, right? So trace Cx is just a linear function of x. C is the input of the problem. And you have some linear constraints in the form of trace Ajx is smaller than Bj. So the input of the problem are n by n. We assume that they are S-sparse matrices C, A1, AM. S-sparse means that there is at most S non-zero elements in each row of the matrix. And we have these M real numbers, B1, Bm. And we have an R, which is like an upper bound on the trace of the optimal solution. So you can ignore this R, this is just to state the correct result later, but that's not so important. And the outputs, we want to output a matrix X, which achieves the optimal here. Okay? So that's some abstract problem, right? It's in, maybe in convex optimization.
The R is just a stopping condition.
The R is a promise that you have. So your promise that you have an upper bound on the trace of the optimal solution, which you can always guess and try and then try with a different one, but yeah. So what is a particular case, which is maybe more well known, is linear programming, right? So suppose all matrices are diagonal, the matrix C and A1 to AM. Then you just end up in a system of this form. You have some variables, x1 to xn, which you optimize over. And then you have some linear constraints, right? So linear inequality constraints. So for example, a very easy LP would be this, x1, x2, x3. The first inequality is x1 plus 2, x3 has to be smaller than 1. The other one, x2 minus x3 is smaller than 1, right? And of course, this one you can solve, right, yourself. But if the number of variables start increasing, it gets, right, you have to see how to do it. So what are some applications? Now, this is a general problem, right? So you can map many things to this kind of problem. So like in operations research, people use this out in like on the location problems or scheduling and so on in bioengineering. It's really the best tool we have to approximate some hard combinatorial optimization problems, NP-hard. So of course, to solve them exactly, we think is impossible because it's NP-hard, but we can solve as well as we can. And the best algorithm to solve them usually is a SDP, is a semi-definite programming. So, and so on. In quantum information also, they appear very often. And a nice thing about them is that classically, there are pretty good algorithms, right? So there is two classes of algorithms. One is called interior points, and that's the complexity. Okay, it's like M is the number of constraints. Remember, N is the dimension, S is the sparsity. So it's like M squared and S log R over epsilon is the accuracy you solve the problem. You want to compute a solution which is epsilon close to the true one. And there is another class of methods which is better that depends in terms of M, N, and S, but is worse in terms of 1 over error, right? R of epsilon. So this is what we know classically, and the question is if quantum can help, right? Is this another application that we can have of quantum computation? And then I want to give you two views of that. So first, I want to argue that maybe, yes, quantum should help, right? Because this linear program is a generalization of linear equations, right? Where instead of inequalities, we have equalities, right? And we do know that in the right formulation, there is exponential speedups for these linear equation problems, right? This is work by Heron, Hasidin, and Lloyd, 2008. Also, these STPs, they are very natural in quantum mechanics, right? There is a very natural formulation of them using the formalism of quantum mechanics. So they can be reduced to the following problem, meaning that anything of this form can be efficiently casted as a problem, as the following problem. We are given Hermitian matrices A1, AM, and real numbers B1, Bm, and we want to find a density matrix, right? Just a mixed quantum state, rho, such that the expectation value of the observable AI on the quantum state rho is smaller, than some threshold Bi. Okay, so basically just giving some observables, is there a quantum state for which the expectation value are smaller than some numbers that we are given, B1 to Bm, right? So that's, it seems there's this natural formulation in quantum mechanics, so maybe quantum mechanics can help to solve. But also maybe not. So there is a quantum lower bound of the form square root of n plus square root of m in what we call standard oracle. I'll explain what this is. So if you just so we won't have like exponential speedups in general, right? Remember, this is the dimension and this is the number of constraints. And even these polynomial speedups, people tried before, but it wasn't clear how to do it. But then this is what we study, and I want to show you that we can have some speedup, and what is a speedup depends on how you phrase the problem. But what I think is interesting is that we get it by connecting the problem to the preparation of thermal states, of Gibbs states on a quantum computer, right? Which is also an interesting problem. So, what I want to do is to tell you how this is done. But before that, I want to, just as a motivation, first discuss a little bit about computing thermal properties on a quantum computer. And then second, just tell you a little bit about this linear equation solver, right, as some warm-up, right? So let's see some previous quantum algorithms. So the first example of quantum algorithms is just, let's go back to this Feynman vision, right? Let's see how we can simulate quantum physics on the quantum computer. And there are many things usually we want to understand about the physical system, right? So we're given some Hamiltonian H, describe the physics we're interested at, the model that we care about. And maybe we want to compute dynamics. Maybe we want to solve Schrodinger equation, right? And then for this, quantum computers are great, because what we do, we just have this Hamiltonian, usually has some locality structure, right? Almost always. We look at the unitary dynamics. We break it up into a quantum circuit, into these small interactions. There are very efficient ways of doing that that we learn. We have optimized over time, and we just implement these quantum circuits. And then in the end, we have the output state of the dynamics. We can compute, right, some local observable, something like that. So that's maybe the killer application, right, of the quantum computer. But many times we want equilibrium properties, right? So maybe we want the ground states, the lowest energy states, and they compute the lowest energy. And then we cannot always solve that on the quantum computer. That actually is a very hard computational problem in general. It's like NP hard. It's even harder than NP. But many times you can do that. There are methods or heuristics to do that we think might work well in many cases. But the case I want to consider is thermal states. So we assume that our system is at equilibrium with some Beth at some inverse temperature beta, and that should describe the state of the system. And I want to find a way of preparing these quantum states on the quantum computer, or at least compute expectation values of it, right? So maybe we want to compute the energy or some correlation function or the partition function of some Hamiltonian at some temperature beta. Right. So how can we prepare these thermal states, right? So the worst case, you can show Sharpe hard. So this is even bigger than NP. So no, we believe there is no algorithm, right? So it would be very surprising if there is a general method of doing that. Of course, classically, people, yes.
This is for general Hamiltonian, right?
Local, yeah, general local Hamiltonians. Even in 2 dimensions is already. For 1-dimensional models at finite temperature, it's easy. Okay. In 2 dimensions, the worst case is already very hard.
But for local Hamiltonian?
Yes, nearest neighbor local to the lattice, square lattice. Of course, right, people care about this problem in physics, right? So they develop good classical methods. Maybe the most powerful one is quantum Monte Carlo, I mentioned before. So this is a classical numerical method, but it works well, but there is restrictions. So it practically works well if there is no sign problem. So I don't want to explain what this is, but for example, for bosons, it usually works well. If there is frustration, sometimes it doesn't work so well. And for fermions, it usually fails, right? So there's some class of systems for which it's fine, but it's not a general method again. But now if you really have a physical system, a quantum computer, for example, you could let it thermalize, right? You just consider open system equilibration, and we think, right, after some time, we'll get there. But of course, maybe the bath has to be very big. Maybe it's a spin glass and it will not go to the thermal state and so on, right? Then people explore more like quantum algorithms approach to this, and we might explore use some of them, but so let's review very quickly. One is this called amplitude amplification. It's basically a version of Grover, okay? It's a version of Grover which is more general. And then you can solve remember, n is the dimension of the matrix, so now n is the dimension of the Hamiltonian, meaning that log n is the number of qubits. So in time n, this is exponential, you can always do, right, trivially. But now using Grover, you can get a square root speedups here too on a quantum computer. So the worst case, you can always solve in types square root n s sparsity of the model, right? If it's a local model, it's very small. Then, okay, this is a speedup, but it's a quadratic speedup, right? It's still exponential in the number of qubits. Can we do something better? People look at versions of the classical metropolis algorithm, which is the best thing to simulate thermal systems in the quantum case. Basically, they consider Markov chain on eigenstates of the Hamiltonian. And that's nice, you can run if you have a quantum computer, but it's kind of a heuristic, as is metropolis, classical metropolis. So the convergence is unclear, right? It works like high temperature, but we don't know at low temperature, which usually we care about. There's other methods, you can try some other things. Let me jump this, but again, so the bottom line, this is an interesting problem. There is some things we can try. There is no solution in general, but some heuristics that we have classically, we have quantum as well. So this is one direction that we could go. Let me consider another example of quantum algorithms, and this is kind of cleaner in a sense, which is this task, very easy task, very simple task of solving a linear system of equations. So imagine that you have a matrix A, and let's suppose it's n by n square for simplicity, and even Hermitian, okay, just to make it easy. And then we want to find an x such that ax equals b. And we also given b, which is this vector of n numbers. So what is the solution? If A is invertible, it's just A inverse applied to B, right? Easy, right? We do it all the time. But if A is an n by n matrix, it's clear that we need time at least n, right? Even to write down the solution, right? So we cannot solve this in time less than n. Usually we need more than n, right? But actually, for interesting matrices, people can get very close to n, which is surprising already, but that's definitely a limitation, n. And what Herm, Hasidin, and Lloyd found out is that actually with a quantum computer you can do better. So there is a quantum linear equation solver that does the following. So suppose that let's see A as some Hamiltonian now, okay? And suppose they can implement the time evolution of the Hamiltonian efficiently on your quantum computer. And you can do that, for example, if A is a local Hamiltonian, right? So, or even if it's just a sparse Hamiltonian, there are efficient methods for doing that. And suppose, actually now you change the problem a little bit. You are given this B, which is a vector, as a quantum state. So now the components of B are the coefficients of the quantum states in the computational basis, for example. Then you can prepare the solution, again as a quantum state, in the amplitudes of the quantum states, x, which is, this should be proportional to this, right, because it might not be normalized, in time polylogarithmic in n and 1 over accuracy delta. So, right, so we get exponential speed up in terms of n. Times S, which is the sparsity of A, and kappa is the condition number of A. Okay, so the condition number is the top eigenvalue divided by the minimum eigenvalue. So if the condition number is not too big, and if you are happy to have this be in quantum form, then right, this gives big speedups. So the input is in quantum form, right? So meaning it's given as a quantum state. So maybe you say it's not so fair to compare classically, but
how is this problem different from just diagonalizing the matrix? Are you getting some new information, or is it a different way of diagonalizing?
Well, it's you require less than diagonalizing the matrix, right? So because you just want to output x, right? You don't need to output the eigenvalues of A and the eigenstates of A, right? Of course, if you can diagonalize, then it's easy to do this inversion, right? Because you can just invert the eigenvalues and multiply them, right? You could say like that, yeah. That it's indeed it's a simpler task than diagonalizing the matrix, yeah. Yes.
Can this time be at any parameters greater than the time we had before? I mean, this polylogarithm of n
Yeah.
would be greater than n times to
No, I mean you're comparing. Maybe not. Classically, you need time at least n. quantum, they found that it's like log n. I can even tell it's like to the power of 3, I guess. Was this a question? So, right, so this is much smaller, right? Right, sorry, maybe this confusing notation I'm using, but it's really concrete like that, right? It's just like log n to the power of 3, right? So this might have many applications, of course, because we use this, right, linear algebra all the time. So if you want to solve linear differential equations, you can do it. If you want to just compute, for example, people found out like for electromagnetics scattering cross-section, they initialize this algorithm and saw some speedups. Machine learning is used a lot, and so on, right? So also in a sense, the question we are considering is, let's look at generalization of linear system, right, which worked for quantum mechanics, which is linear programming. So now it's an inequality instead of equality. Sorry, do we have a speed up? Right, so that's the question.
So,
Yes.
in the classical problem, you want to find the coefficients of x, but in the quantum version, you prepare a quantum state.
Correct.
Don't you need to measure the quantum
Yeah.
state to find? So doesn't this
Is that,
breaks up this?
yeah, it's a great question. Yeah, so so the question is just, let me rephrase, right? Let me say again. What you output in the quantum case is not a list of, it's not a piece of paper with n numbers where each number is xi, right? The components of x, right? This of course will take time n, right? It's just a quantum state for which the amplitudes is given by the xi's. And of course, this is less than what you ask from the classical solver, right? So that's true, and that's a limitation of the method. But the idea is that maybe, what you want to compute is not all the components of x, but maybe you're happy to compute some linear function of x, right? Maybe something like this, like, something of this form. And then you can do that efficiently on the quantum computer, right? And what they show is that even this version where you just want to compute functions of the output and not the output entirely, this is actually a complete problem for quantum computation. So in the sense that if you can do that classically efficiently, you can solve any problem in quantum computing, any problem in quantum mechanics, in many-body quantum mechanics efficiently as well. So in a sense, that's like the hardest problem that the quantum computer can solve as well. But yeah, but it's true. A big caveat is exactly this: quantum input and output, right? It's like in quantum form, so you have to be careful. But let's go back to whether quantum can help for semi-definite programming, right? And now let me show you this connection to the preparation of Gibbs states on the quantum computer. And how we see a connection? Well, that's just basically statistical physics, right? So we know since a long time from James that there should be a connection. So let me just remind you what is these results. It's also called principle of maximum entropy, right, in statistical mechanics. The quantum version says that let rho be a density matrix, is a mixed quantum state, such that we have some observables AI, Hermitian matrices, and the trace AI rho equals Ci. Right, so we have a state and has some expectation value on some observables AI. Then the principle says that there is a Gibbs state, so there is a state of this form, exponential, a Gibbs state of a Hamiltonian, and the Hamiltonian is like sum over I, lambda I, AI. Lambda I are real numbers, for which this Gibbs state has the same expectation values as rho, okay? So why this? Of course, any density matrix can be written as a Gibbs state of some Hamiltonian, right? The Hamiltonian is just log rho, right? But here is special because the Hamiltonian is just a linear combination of the observables you care about, right? So if you only care about one observable, there will be just here really the same observable, some temperature. If there is only two observables, it's a two-parameter space that you have to look at, right? So the task is have to find these lambda i's, but there exist lambda i's for which these two have the same expectation values. So all you care about are expectation values according to this observable. You can just think your state was this one, right? It makes no difference. So that's what it's saying. This Gibbs state, moreover, we know is the state of maximum von Neumann entropy with the same expectation values as rho. We won't use that. That's why it's called principle of maximum entropy. And this connection that I'm going to see how this applies to SCP next slides actually was used by the classical people before to come up with this multiplicative weight method for SCPs. And people used before like to study quantum complexity theory, but not for quantum algorithms. Okay, so why this is useful for us? This is the problem that we have, right? We want to solve this problem, so we just want to find an x which satisfies these constraints and which maximize trace Cx. So let's just take optimal x, right? So we take, so I will claim that by James' principle, there is a solution of this problem of this form. Exponential sum j, lambda j, aj plus lambda 0 c. Where these lambda j are real numbers that we have to find what they are. Why? Well, let's just take an optimal solution, x optimal. It must exist, one, right? We assume. We normalize it. it's a quantum state, we can apply James' principle where the observables are C and the AJs. Then the James' principle gives a Gibbs state whose Hamiltonian is a linear combination of the input matrices, which has the same expectation values. But the Gibbs state by construction is positive semi-definite, right? All eigenvalues are equal or bigger than 0. And of course satisfies the constraints because, right, they only care about expectation values. So this Gibbs state that we get from James' principle must be an optimal solution as well, right? So that's it. So there must be an optimal solution of this form, and therefore we just have to find this lambda j. We have to find a way to find these lambda j's, right? So this you can already see how we can try to solve that on a quantum computer. So we just use some kind of interactive method where each time we guess these lambda j's, then we build on the quantum computer these Gibbs states, right? So we prepare the Gibbs state using some quantum algorithm, or just let it, this Hamiltonian equilibrates. Then we measure these AJs, which are Hermitian matrices, as observables, get the values. Then we do some optimization, try to find a new guess for lambda j, and we keep going, right? And I claim, it's not clear, that this will give some speed up. Okay, so let me tell you one result and then we get to the details. So I will show you that there is a quantum algorithm for solving these SCPs, and the runtime is C Gibbs, is something related to preparing the Gibbs states, I'll get to that, plus square root m. M is the number of constraints, so we have a mild speed up in terms of m, but maybe a big in terms of n, I'll tell you, and some polynomial in sparsity and one over error, R over error. So the input is the same as before, are the matrices and the numbers. There is some normalization, do not pay too much attention to that. That's just to determine the scale of the problem. What is interesting is that, again, as in linear equations, the output cannot be the matrix written in a piece of paper, right? Because this would take time n squared, right? These are n by n matrix. So we have to allow something, for something less than that. So we are happy just to output quantum samples of the optimal matrix. So we should be able to prepare a density matrix, which is a normalized version of the optimal solution. We should be able to output the optimal value. Optimal value is just the value of trace Cx after some small error, and the output also the trace of x. Okay, so this is what we require from the algorithm. It's less than writing a piece of paper, but if you want to speed up, so we have to do that, right? So the input model, well, is the same as people usually use for Hamiltonian simulation. We just assume there is an efficient function, an oracle, that's just an efficient way that given a choice of the matrix, a choice of the row, and a choice of the elf non-zero elements in that row outputs the matrix element there, right? So we just assume that there is some structure in these matrices that we can do this computation efficiently at unit cost, right? And then we have these results. What is C Gibbs? That's the important thing. That's just the time it takes to prepare on a quantum computer using whatever method you want to use, and I'm going to specify how we're going to do that in the next slides. Gibbs states of this form, right? So we think we have some input matrices. This comes from the problem. This defines a class of Hamiltonians, right, where we can find these UIs. And we see what is the fastest way we can prepare this kind of Gibbs states. And this basically is the leading complexity of the method, right? The faster we can prepare the Gibbs states, the faster we can solve the problem. There is these numbers here, right, and they matter too, of course. So in initial work of myself and Chris's work, we found C Gibbs times square root of m sparsity squared, and it's horrible dependence on one of error, right? Like really, right? There was some maybe speed up here, but of course you never use that. Then some people, so Appledon, Gillian, Gibrin, De Wolf, they improved that a lot to error to the 8. It's still not great, but better. Then with Kalev, Lee, Lin, Svor, and Wu, we found that actually can be the sum of C Gibbs and square root of m and r epsilon to the 8 as before. And later, Appledon and Gillian improved to r over epsilon to the 4. So right, so this dependence, which is kind of a limitation of the math, is getting better and better, but I don't know what we should expect. But what is the point? Is that now we can use all these methods for Gibbs sampling that I mentioned before, like quantum metropolis, for example, at least to run this as a heuristic, right? And if thermalization is quick, which many times it is, but not always, it depends on the model that we have here, then we might get some big speed ups, right, over a classical solver. Okay, so let me jump this. I'll go back to this later. I want to go back now to this near-term application, right, which is what I mentioned before. So I'll try to convince you now that this SCPs is something that we should try in these near-term quantum computers that we might have next year. And then maybe this is a good place tries to say speed up. So let's see why. So first, let's use a simpler version of the algorithm that I haven't told you what it is yet, but believe me that it's like that, where we do not have a speed up in terms of m, the number of constraints, but we still might have something in terms of the dimension of the matrix. So the complexity in that case is T Gibbs, m over epsilon squared. Then in that case, why that's nice? Well, because the quantum part is very simple. So the quantum part is just used to compute the expectation value of the input matrices, AI, on some Gibbs states, right, which is a linear combination, whose Hamiltonian is linear combination of this matrix. And that's something that we can try to run on these small quantum computers. So the idea of the algorithm will be that we have some number of iterations, T, from 1 up to 8 log n over epsilon squared. This is a very small number, right? It just goes with log n. And it's the following. So the method is the following. So we have a quantum computer and a classical computer. At some point, the classical computer computes some coefficients, real numbers, nu I t at round t. This is fed into the quantum computer. In the quantum computer, we switch on a Hamiltonian given by this sum over I nu I t ai. Okay, that's Hermitian matrix, right? It's a Hamiltonian. Then, using some methods, we prepare these Gibbs states. Okay, so this is just exponential of the Hamiltonian over partition function. We compute the expectation value with each AA. This is called CAT, is the expectation values. This is sent to the classical computer. There is a very easy computation to do here. You compute nu I t plus 1, and you keep doing that. And I claim that after a short time, log n, this works. It outputs the right solution.
So the optimization of the real parameters is done on a classical computer. Right?
Of which parameters?
So I mean, so the lambdas now are the news, right?
Yeah, that's right.
And this is optimized.
No, these news are computed on the classical computer from information about the CITs. Yeah, that's right. Now we want to run this on a small quantum computer. And the point there, yes.
The solution is what here?
The solution will be density matrix is in this form that I mentioned. Let me go back. The solution is like that. It's a density matrix, right? It's a mixed state of this form, such that this X optimizes this, right? It's the best, right. So now we want to run this on a quantum computer. And of course, ideally we like to have a solver for every input matrix that we want AI, right? And if you had a universal quantum computer, you could do that. But we're not there yet. So now what I'm going to do is just to say, okay, so now we just, maybe I don't want to solve STPs in general. I just want to have some instance of STPs for which I can solve much faster than classical computing. And then I declare victory already, right? I just say, okay, maybe, right, it's not for your STP you want to solve, but there is one for which is much faster. And that will be a good enough indication that we are on the right track, right, for useful applications for quantum computing. So in the near term, right, the proposal is to solve this semi-definite programming, which might not be of practical interest. This instance, right, the instance is specified by the matrix AI and C, right? So you can choose them. So I'm going to choose them in a good way, which is suitable for the quantum computer that we have available at the moment, right? In particular, right, so let's look at Google's they have a superconducting qubit platform. So this is a 9-qubit version of it. Now they are working on the 72 qubit version, right? So I don't tell too much the physics, but basically what they have is just, they have some islands, superconducting islands, and they put some justful junction in the middle, and then Cooper pairs can tunnel through it, but it's like a condensate. So there is like a conjugate variables, which is the number of Cooper pairs in the island and the phase, right, of this condensate. And this is like X and P. And then they can define a Hamiltonian, a qubit using basically this X and this N and the phase, right? They actually, you put some nonlinearity in the circuit here, so they have a nonlinear spectrum, and therefore you can do that. So if you put everything together, you find that the Hamiltonian on all the qubits is described very well by what we call Bose-Harbert model, right? So this is a model of bosons. Nj is the chemical potential, so that just counts the number of bosons on site J. So we have some chemical potential and delta J, which can vary from site to site, so that's nice. We have a nonlinearity, so we have a repulsion term which is equal to n times n minus 1. So if there is more than 2 bosons on the same side, there is repulsion, there is a penalty. And we have tunneling, right? These bosons can hop from one side to the neighboring one. And a nice thing about Google's experiments is that all these coefficients, delta, eta, and g, they are freely, they can tune them in any way they want, okay? So, so my proposal, what I would like to try is just, we build a STP for which the instance is the matrix A0 is identity, B0 is 1. You just say the optimal solution is a density matrix, makes it easier. And the other AIs, they are just both Harvard Hamiltonians with different choice for delta, eta, and g, okay? Why that's nice? Well, that's nice for the quantum computer because then we should only be able to use it to compute thermal expectation values of the Bose-Harvard model for some choice of these coefficients, right? Because linear combination of them is again just another Bose-Harvard model, but with different coefficients, right? So basically, if we can compute local, and this AI, right, it's the sum of local observables. So if you can basically compute local expectation value of local observables on thermal states of the Bose-Harvard Hamiltonian, we will be in place, right? So that's the proposal. So, but now how to do that, right? One idea is just, okay, let it thermalize. But that's not really good because the temperature is the temperature of the fridge, right, where these qubits are there, and we do not control it, right? And we need some control over temperature. So I want to use basically dynamic equilibration, right? So I want to implement coherent evolution according to this Hamiltonian until the system equilibrates locally. Okay, it's a pure state, but locally it will equilibrates. So I'll tell you more detail in the next slide. Now, why we should do that instead of just maybe quantum annealing? The point is that they have a lot of control over these numbers. So G can be negative, and this will be the case, for example, in optical lattice. It's like kinetic energy. But actually, because this is superconducting qubit, it can be positive as well. And if it's positive, it defeats quantum Monte Carlo. Okay, it becomes like a problem with a sign problem. So there is we do not know currently how to compute these things classically, right? And that's good for us.
Sorry, what are you creating or destroying? What are these creation and annihilation operators?
Yeah, that's the number. That's the number of Cooper pairs in some superconducting islands. That's what it counts.
L and K or what?
Oh yeah, L and K are just so this is the number of sites, right? And L and K just run over neighboring sites. And I didn't put a picture, but the 72 are kind of a 2D square lattice, so it's between the nearest neighbor there.
And you can create the states in the device. You can do it.
Well, the device is described by this Hamiltonian, right? And now the point is how we create, for example, this Gibbs state there, right? Or how we just compute this function, right, in the device. So this is what I want to tell you how to do now. So indeed, one idea would be just to we know we can create this Hamiltonian there because we can control G, eta, and delta the way we want. So we create it there. We could let it equilibrate, but if we let it equilibrate, it will go, we think, we don't know for sure, but we might go to a Gibbs state, but at the wrong temperature, right? So that's the challenge. Yes?
Directly measure those coefficients? You can change their value, but can you directly measure individually?
These guys?
The G, eta, and delta.
Oh, this, yes, but you can control in the sense that these are specified, for example, by the voltage that you put here, and there's a lot of wirings there. And
you can adjust, but can you correctly measure and say, look, this is the value of G? Or can you just say, well, it's...
So it's a good question, and actually, yes, there is a way to benchmark the values there, and usually they indeed see that they try to have specified values of them, but they have some error there, right? But they can, and that's the way they actually do it. Afterwards they measure them. There is ways to measure them, and then they find, oh, actually what the implement was, right? Delta plus some small deviation, but they can find out, yeah, some accuracy.
Sorry.
Yes.
Why do you mean by Gibbs state with the wrong temperature?
I mean that suppose you create this Hamiltonian there, okay? Just by engineering these couplings, you can do that, and then you let it equilibrate. But now it goes to the temperature of the bath of the fridge, right? And this fridge has some temperature, right, which you cannot control. So you get this state, but with a beta here, the inverse temperature. And that's not good, right, because we want when beta is 1 here, for example. So that's the challenge.
So you chose B0 to be 1, but what about the others BI?
Yes, these BIs, that's right. It would work for any values of them, yeah.
So you want to control the A's in order to balance the temp, because you should have a beta. There you have a beta equals 1.
Yeah.
But you have, the system has the temperature of the bath, so you want to tune the deltas and etas.
No. That's right. I want to do something else. So I want to, something like this could work too, but there's some drawbacks, but I want to do something else. I want to keep everything coherent I want to say, okay, these systems, they are very coherent. That's the point, right? They don't interact a lot with the depth, at least if the evolution is not too long. So I want to keep everything coherent. So the total quantum state will be pure, but I will claim that if you compute on this pure state, which is just some dynamical version of this Hamiltonian, it locally goes to a thermal state. So I'll tell you now in the next slide. So just a sec. Yes.
But then, so the AIs, so you're assuming that they're local here.
Well, they are sum of locals, right? So we can compute each term, right? This is local, this is local, this is local, right?
I see.
So with local tomography, we
So
can
you
do
won't
that.
you won't need to go to full tomographic reconstruction.
Exactly, yeah. And that's very important, of course, as well, right? Okay, so just what I said, you could couple to BEF, but then you need tunable temperature. And if you want accuracy delta, temperature has to be as low as delta square. So maybe that's good if you have an annealer, but you need this control of temperature that at least at Google's we do not have. So this is the idea I want to do. I want to look at dynamical thermalization, which is anyway an interesting idea to explore on these small quantum computers, right? Like this idea of phases of dynamical system in quantum system, whether you have many bilocalization or chaos and so on. This is a new area, it's not well understood, and I think these small quantum computers can elucidate many questions there. But specifically, suppose you have this Hamiltonian. This comes right from the SDP solver. The lambda i's are given to us, we find what they are, and we want to prepare basically the Gibbs state of this guy at temperature 1, right, to compute some expectation value. But now we want to do it by coherent dynamics. And what is the idea? Suppose H is ergodic, like quantum chaotic, and this Bose-Hubbard model, we don't know if it's in 2 dimensions, but in 1 dimension, where it's easy, we can do numerics, and if there is no disorder in the coefficients, it is chaotic, it's ergodic. Then what will happen? It will happen that after some time, after the calibration time, which is short, so we could, the error wouldn't add up too much. Because this AI is a sum of local terms, the expectation value of this pure states actually is very close to the expectation value of the equilibrium states, where the energy of the equilibrium state is the same as the energy of the initial states. So we just prepare initial state, which is like a product state. Okay, it's a very easy state to prepare, which matches the energy of this thermal state at temperature 1. And then we let it run the dynamics. And then, because we expect some virtual quantum chaos here, the system to be ergodic, it will go to the thermal expectation values there, right? So that's a way of getting thermalization without having to have the global Gibbs states. We just have it locally. But that's good enough for us, right? We can use that and then run the rest of the algorithm. So there are many questions, of course. First, in 2 dimensions, it's ergodic. It is in 2 dimensions. In 1 dimension, the system is ergodic, this Bose-Hubbard. Is that so in 2D? We don't know. We cannot simulate it classically. So maybe we have to wait, right? So in that sense, it's a heuristic. But we expect it to be, right? So I'm running out of time. Let me just, well, maybe I have to,
So
yes.
maybe 5 minutes. Start as you say.
5 minutes? Okay, so yeah, so I'll just 2 slides and then conclusion, so it should be okay. Well, what I haven't told you, but you just ask me later if you want, is what is the complexity if you have a universal quantum computer, for example, right? So we also work this out, but that's maybe, we have time for that, right? Because we don't have the quantum computer yet. But anyway, so for the annealing, so what is the relation of this kind of quantum SDP solver and this traditional quantum annealing that there is a lot of work on it? So let's look at a very simple SCP. It's just to compute the maximum eigenvalue of a Hermitian matrix C. This is the following SCP. We maximize trace Cx such that trace X is 1 and X is positive semi-definite, right? So X is Hermitian, so it's clear that the best thing you can do here is just to put X equals to the projector onto the top eigenvector of C, right? So that's why in this way we are computing the maximum eigenvalue. And that's the problem of quantum annealing, right? In quantum annealing we have some C, which is like some maybe classical Hamiltonian, some spin glass, which we want to compute the ground state energy, right? Because this encodes some combinatorial problem that we want to solve, like max cuts, for example. So, this is a particular case of the SCP, right? And this will be an example, right? So if you have a graph, you want to find the maximum cuts, then this is the cost function, some classical Hamiltonian, and we want to compute the maximum eigenvalue here, right? The maximum eigenvalue is directly related to the cuts, but that's more general. And people study this a lot, right? So basically the idea is that the final Hamiltonian of the quantum system is minus C. The initial Hamiltonian is maybe all qubits in the X basis. So it's like sigma X everywhere. And now adiabatic you change one to the other, and you hope that by the adiabatic theorem, in the end, you're in the ground states of the C. The trouble here, of course, is that the gap might close, right? And it usually closes. And more importantly, quantum Monte Carlo, because of the choice of the Hamiltonians, the final is classical, quantum Monte Carlo actually does a good job here, right? There's no sign problem. So what people realize is that this minimum gap is very much related to the convergence time of quantum Monte Carlo. So that's the limitation here. And let's see if we can go beyond that. So I want to compare quantum annealing versus this quantum SDP, this approach that we are studying. So the Hamiltonian in quantum annealing, it's classical, right? We care about a classical Hamiltonian, diagonal in the computational basis. What is nice here is that we allow any quantum Hamiltonian make sense for STPs, right? The temperature for annealing should ideally be 0. For STPs, we have a good control. If you want to error delta, temperature can be like order delta square. So maybe it's a little bit more robust. Preparation for annealing can do cooling, of course. Adiabatic evolution is the usual choice. There is this quantum approximate optimization algorithm, some digital version of adiabatic evolution can be used. So STPs, we can do cooling, as I mentioned, and we can do this dynamic equilibration, right? Which I think it's an interesting idea to explore in the near term. So what is the runtime? Again, both, they have this thing that we have to compute. For quantum annealing, is the minimum gap in the adiabatic evolution. This might be exponential, it's always a problem. For us, is the thermalization time, is C Gibbs, right? And again, this might be big, but if it's not, then, right, it's good. Yes?
The temperature, this delta squared, you mean the temperature of the real bath?
The temperature of the real bath, if you would do cooling in it, yes. I guess maybe the main point of the talk is that these quantum SDP solvers, they explore more fully the quantum features of the device, right? Because you can have these general quantum Hamiltonians, and then they can beat quantum Monte Carlo more easily, and therefore I think that's why I think there might be something worth trying in the near term. So this is the algorithm. I hope you understood what it is. So let's let's go to the conclusion. So that we have these non-quantum algorithms, right? And they already make it worth building a quantum computer. But of course, we would like to have more. And that's not such an easy task, right? So usually it's challenged to come up with new quantum algorithms. First, because we don't have a quantum computer yet, right? So it's very hard to test and gain intuition, right? So it's the same thing, say, okay, how many of the great classical algorithms we had before actually having the classical computer? A few, but not many, right? And on the other hand, we must compete with decades of advancing classical algorithms, right? So it's not enough to come up with a good algorithm. It has to be better than any classical one, right? Of course, we have quantum mechanics to our advantage, so that's why sometimes you can do it. So the point of the talk was that exploring quantum semi-definite programming solvers involve an interesting combination of different quantum algorithm frontiers. So there is a little bit of this HHL, these linear equations, right? It's a generalization of it. It's a little bit of quantum metropolis, which is about preparing Gibbs states, and about quantum annealing, in a sense, is also an extension of it, and has the same feature that we can try in the near term, right? So the bigger open question for me is, are these STPs like the killer application for this NISQ device, right? Is this what we should try and really get some good evidence that we are doing, that they are already interesting from a computational point of view? And if it fails, right, of course, the question that everyone in the field cares about at the moment is, are there any application of this NISQ device, right? Are they, there's anything you can do with them beyond achieving quantum supremacy, right? So I think, and if you have any idea, let me know. So that's all. Thank you.
Thank you very much. Do we have questions?
Hi, thank you. Building on what you said in the last part, we need to build a quantum computer to be able to test those algorithms. What have we achieved so far in building quantum computers? I read something, maybe wrongfully so, that I think we already achieved something around 15 qubits. Is that correct? Or if not, what could we envision for the short term in terms of building quantum computers?
Yeah, so it's a good question, because to answer the question, it's not just about the number of qubits, it's about the number of qubits and the error rates that you have there, right? So let's go to one extreme. So people have optimized and then there's this company, D-Wave, they have the records, they have like 2,000 qubits, but they are very noisy, so they're not, you cannot really use them, right? So in that case, you have to be very careful to have a good control. Then there's another direction where people that study optical lattice, for example, then they really have a lot of qubits, also like several hundreds, but they cannot measure the qubits individually. There is very little control there. And then they can already do some interesting quantum dynamics that we don't know how to simulate classically, like related to many-body localization, for example. So you could see that in the direction of quantum simulators. There's already like quite a large number of qubits. But now really in the close to quantum computing, we would like to have large number of qubits, being able to have like circuit model, right, 2-qubit gates and so on, and very low error rates. And now we have that so far with order like maybe 30, 25 qubits and error rates of 1%. But there is we're on the verge of having, right, maybe this year, maybe next year, the plan, unless something really wrong happens, is to have 72 qubits and 2-qubit error rate of 0.5%. And then we get to this regime where, simply we do not know how to simulate anymore this device, right? The best classical method on a supercomputer takes weeks, on the quantum computer takes 1 second or milliseconds, right? So I think we're just at the verge where something interesting might be able to happen, but right, yeah, it's.
So thank you very much for the nice talk. So I guess that you will try to prove quantum supremacy by brute force, right? So you will run these SDPs, these quantum SDP solvers, and you will compare with some classical supercomputer, right?
That's right.
So I'm curious about what's the figure of merit that you will use for that comparison, right?
Because sorry, what is what?
What's the figure of merit that you will use for that comparison? Because on the one hand, you will be running an experiment where you will be doing this local tomography to come up with the expectation values of the observables for the SDPs.
Yes.
And on the quantum and on the classical computer, you can do really the count of how many classical gates you apply, or are you just going to compare the total runtime of the classical computer? How are you going to compare those?
Yeah, it's a good question. There are many different ways you can compare. But I think if you just compare, for example, the total runtime, and let's just, let's give everything you want, the supercomputer, total runtime, the quantum be the things that's on, unless if the error is not a big problem here that we don't know yet, but we expect it maybe not to be given the error rates. The quantum computer will solve this will be like milliseconds, right? Because it's very few interactions, and each time for the quantum computation takes like a few milliseconds, and the best supercomputer in the world will take like weeks. So it's like such a big separation that the details, I think, will not matter so much. Right?
But then also the measurement process will be automatized in the quantum computer, right?
That's right.
Okay.
Yeah.
Right.
Well, no, but the classical computer, measure local tomography, send to the classical computer, compute the new Hamiltonian, right? And
right.
Yeah.
Okay.
Right.
Cool.
Yes.
Thanks.
Any further questions?
So in the beginning, you said that factoring scales like exponential to the n 1/3. But given the prime factors, it is easy to verify that they are correct.
Correct.
So does this imply that factoring is in NP?
Factoring is in NP, yes.
But given that you have Shor algorithms, doesn't this imply that?
No, because it's not NP hard. It's not NP hard.
Right?
Yes, that's
okay.
right. Yes,
Thanks.
that's right. Yeah.
Sorry.
Yeah.
So, Brandão, my question is, in the HHL algorithm, there are several constraints, right? Like the sparsity of the matrix and the condition number. In your case, that you do a combination of that, this restriction is still there?
Yeah, it's just because in this heuristic version, everything is built in Gibbs, right? But if the slide that I jumped, if you go on a universal quantum computer, right? So this would be the thing, right? Using no method. So either it would, like in HHL, when they input this quantum form, you would have this kind of complexity. Like it will be exponentially speed up in terms of n, but then the condition number now becomes some parameter b, which is related to the trace of the input matrices, right? And then you have this dependence on sparsity as well, S square, and this dependence on error, like this one here. So then, on the universal quantum computer, you have similar parameters that you have to optimize, like something that is associated to is kind of like the analog of condition number, the error is there, and then the dimension, and so that will be the complexity on the universal quantum computer if you have quantum input data, and if you don't, it's something like that. So
I have another question is about the isomorphism problem, the graphs. Do you think that quantum computers can do better with the classical?
Yeah, unfortunately, it's not so interesting anymore because there is this quasi-polynomial time algorithm now by Babai, right? So it's not classical yet. Of course, it's like n to the power of log n. But because there is now, the guess is that there is a classical efficient algorithm as well, right? So after that, I think, I don't know if it's the best thing to look at for quantum speedups. Yeah.
So I had the question about, I guess related to Nelson's, but so in high energy physics, the limit is just how much money you can spend on building a bigger accelerator.
Right.
In quantum computing, is it money? Is it, what's the obstacle to building a bigger?
Yeah. So it's a great question, and we are on the way of finding out, I think. But our current view is that it's money.
The money spent on doing what? What do you need to improve?
On, for example, the money, how Google is spending their money. So of course, have to pay us. But apart from that, it has to, build bigger and bigger fridges, right? Because if you have more computing, more qubits, you need these bigger fridges, like a clean room, because you have to compute this to build these superconducting qubits with great coherence properties and so on, right? So it's really, this hardware is expensive, but there's no limit to scalability as far as we know, right? So.
Are there any more questions? All right, I don't see any. So let's thank Fernando again. And there are refreshments upstairs in Mezzanini.